Hello. Hi guys, good morning. Although it is good night, it is 11:19 right now. But firstly, a very big apologies. I was not able to bring the video yesterday. This is of weekly contest, fourth question, which we usually discuss in the contest day itself. But the work is pretty hectic, so this is the only time I could get to actually record the video. But yeah, let's start off. Problem again. Problem 1 and problem 4 we will be discussing in this video. Just problem 4 we will be discussing mainly, but the brute force approach is just the problem 1. So you will discuss both, like you will be having both the problem 1 and problem 4. Now for problem number 2 and problem number 3. Problem 2, after watching this video, or if you have watched any of the try videos, then see problem 2 have two approaches. One is a simple brute force approach, which is also the most optimal one. It's just that it will be 8 into n, but then with a simple try approach you can also solve it. So you can solve it without even try knowledge or with try knowledge also, which means it has two ways to solve it. Again, you can simply solve it even after watching this video or before watching this video also. Again, it's a simple brute force. Now for question number 3, I had just uploaded the video yesterday on the prime number masterclass. You just need to know the sieve, which is the main part of this video. Just watch this video and then you will be able to solve question number 3 also. Now let's come on to the most important question, which is question number 4. So it simply says that we are given a 0 indexed string array called as words. So basically it's a string array. So basically it's an array, and basically each array element is a string like this. Okay, now we define a boolean function is prefix and suffix, and it takes two arguments, which means two strings. And what it tells me is, okay, if it will return me true if and only if string 1 is both prefix and suffix. So basically string 1 is prefix of string 2, and again mark my words, and string 1 is suffix of string 2. What I mean by that is, in the example itself it says, okay, string 1 is, let's say, ABA, and string 2 is ABA BA. Then I can easily see that, okay, string 1 ABA is a prefix ABA in my string 2, and also string 1 ABA is a suffix ABA in my string 2. For a new example, I can just tell you one more example, that string 1 ABC is a prefix, which is ABC in my string 2, and also string 1 ABC is my suffix in my string 2. So if that is the case, then I can simply say that, okay, is prefix and suffix of that argument will return me a true. Now my task is to find out, or basically just tell you that a number of indices, index pairs I and j, such that I is less than j, which means I is less than j is always after I, and also word of I and word of j is true. I have to find or tell you number of all such pairs. Cool. Now the simple, very simple, logical, what the problem is saying, if I implement the exact same stuff, I'll do, okay, I want all the index pairs, which means I can go on to all the index pairs. Okay, I can simply try two for loops, and with those two for loops I can go on to all the index pairs. That will be O of n square. Simple. And then after I have gone to these two indexes, I can simply go and make this function, that, okay, I am at two indexes I and j, I will get words I and words j. Now I have to just check that words I is both prefix and suffix of my word 2. So now if I am at I and j, I will have my word I and word j. Let's name word I as string 1, let's name word I as word j as string 2. Then for sure, simple fact that I have to check if s1 is a prefix of s2, which means the starting portion of the string of s2 should exactly match with s1, and also the ending portion of s2 should exactly match with s1. If that is the case, and if both of them are true, then I can simply say that is prefix and suffix of these two is actually true, and I can simply increment my answer by 1. So you can simply see, to try on for all the ij pairs, you will take O of n square time, because let's imagine your word length, which means you have n strings in the input. As you can see in the input, your word length, you have n strings in the input. Let's imagine that, and let's imagine that each string is of word size s. Each string is of word size s. I'm taking the worst possible case. So I can simply say that to go and try for all the possible pairs, it will take O of n square time. And for a string of length s, this comparison would take O of s time, because you just have to compare the starting portion. Pointer, 2-pointer approach, compare, which means if the string 2 is like this, and string 1 is this, or let's say this, then I have to just use 2 pointers. Okay, compare this. It is done. Okay, no worries. Now go and on the right side, compare this. Simple. A 2-pointer approach will take to just compare these two strings. So it will take O of s time. So you can simply see it will take O of n square into s time. O of n square into s time. Although for the simple approach, O of n square into O of s will actually pass. Simple. It will simple pass for the problem 1. But for problem 2, O of n square into s was a later part thing. O of n square itself would not pass, but make sure always see the constraints, all of them. You will see it says that O of n into s is equal to 5 into 1e5. So if I just plot all the constraints, it says n is 1e5, s is 1e5, and then words of I is just 20 like lowercase English letters, which means just 26 letters. Every character is just 26 letters. And it also says one thing: sum of lengths of all words of I, it does not exceed 5 into 1e5, which means n into s is actually 5 into 1e5. Thus it is very important to know the constraints. By this fact, you might start thinking, oh, I cannot apply n into s. Bro, you can apply n into s, because it is bounded by it is bounded by 5 into 1e5. The problem will not exceed n into s, this multiplication. So for sure, you know one thing, that for sure you can try n into s as an answer. But right now, I have O of n square into s, which will not work. Let's have a quick glance at the code. It's pretty simple. I'll use 2 for loops, I and j, and then for both of them, just make sure that, okay, prefix, which means word j substring starting from 0 of the length of word of I, it should exactly match with my word of I. This is the prefix comparison. I have done prefix comparison. Now compare the suffix part, which means in the words of j, substring, which means ending portion, which means the entire length, which means, let's say if the string s2, which means word of j, if this is this big, I know why my word 1 is of length 3, so I can just land onto this index, and the ending portion will be nothing but the substring, which is of size same as that of string 1. So I just get that and I land onto this in specific index. And if I just do a substring, it will see, if you just pass only I, then what it does is, in C++, it takes everything from that I up till the end. If you pass I and length, then it will take starting from that I index up till that length index, up to that length value. So in this, I applied I and length, but in the later part, which means in the next part when I am comparing suffix, I want up till the length, so I did not pass my length. Although you can pass length also, but that's a overkill. So with that, I can simply compare and increase my answer as soon as both are true and condition. Now the obvious fact is how Aryan you will improvise it. How I will improvise it. Let's first imagine that what we got. So we got a n square into s. Now n square is because of we are actually trying for I into j. S was, I was comparing two strings, which means s1 is the prefix of s2, and I was comparing s1 as the suffix of s1. Now to compare two strings, you remember one thing? To compare two strings, if they are equal, or maybe they are substrings of each other, or maybe they are forming a pattern of each other, or maybe they are inside each other or not, we have 3 algorithms. We have KMP, we have Rabin karp, and we have Z. These compare the strings itself. So I can use any of them, but I cannot go and use any of them inside when I am trying for I and J. I can pre-compute, right? I can pre-compute. Now, pre-computation of a string with other string, which one is the most helpful? Can you use KMP? Aryan, KMP is used when you are fixed with two strings. Okay, if I had to know, let's say string S1 and string S2, if I had to know, okay, S1 and S2, then I can apply KMP and I would know, okay, if S1 is lying inside my S2 or not. But but I will compare S1 and S2 only once, right? And that too only prefix part and suffix part. So there is no point of using KMP itself. Makes sense? Now, other fact was that I have to compare S1 with S2, S3, S4, S5, right? S1, S2, S3, S4, S5, and then same, okay, S2 to S3, S3, S2 to S4, S2 to S5. So I will take two strings, apply KMP on that. That is for sure illogical because I will compare two strings only once and that too only prefix and suffix. If I am using simply two-pointer approach of comparison, I only need to compare prefix and suffix. If that matches, I'm good. So I don't need to overkill by applying a KMP because KMP is used if I want to know the substring inside my actual main string. I don't want that. So, okay, Rabin karp is overkill, out of picture. Now, sorry, my KMP was overkill, so out of picture. Now comes the Rabin karp. Rabin karp is hashing algorithm. So basically, what I can do is, if I am at two values I and j, I don't need to go on to the strings to iterate anything. I can pre-compute the hash. I can pre-compute, okay, string S1. I know the length is, let's say, 4. So I compute the hash of the string. Now I know, okay, I'm comparing S1 and S2. I know S1 is of length 4. So I can say, okay, length 4 hash. What? Give me the hash of length 4. Again, I'll not compute that right now. In O of 1 time, I should be getting what is the hash of this specific thing of starting 4 characters. Give me the hash. Okay, so Aryan, will you store the hash of up till every index? Maybe, maybe not. So how will you find the hash? But before you even think of hash, bro, you are still going on to all the pairs, which means you will find the hash of S1, S2, S1, S3, S1, S4, S1, S5. So the pre-computation which you will do, okay, you will do a pre-computation and you can do a pre-computation of all of these strings. I know the entire length is n into s. Remembered? The entire length is n into s because I have n strings and each string of length s. So it will be n into s, but I also know it is bounded by 5 into 1e5. So for sure, I can tell, okay, what is a one length hash, 2 length hash, 3 length hash, 4 length hash. I can also say, okay, from ending 1 length hash, 2 length hash, 3 length hash, 4 length hash. I can store that in memory, both prefix hash and suffix hash of length, this length 4. Same way I'll do it for S2, same way for S3, same way for S4, same way for S5. With that, I will be very easily be comparing, okay, I want the length 4 hash. I want in S2, I want the length 4 hash because I have done a pre-computation of length 4. I have done a pre-computation of all length hashes from starting and ending. So it's a 2 into n into s computation which I will do, pre-computation which I will do to find the hashes. With that, when it is done, I will be very good to go. Okay. Aryan, that sounds great. Okay, for hashing portion, you can actually optimize that to O of 1 while you are computing the hash. So by simple hashing, let's imagine you make a very good hash function, and by the hashing you have optimized that comparison of two strings to know if S1 is actually a prefix and suffix of S2. You will take O of 1 time. So you have reduced the O of S complexity, right, to O of 1. But still, bro, main factor was O of n square. If you compare still I and j, you will still take O of n square time. You have to bring that to O of n. And bro, if you even bring that to O of n, you can still use O of s in the later part, because you remembered, I can still work with O of n into s complexity, right? But O of n square, I cannot work with it. I can work with this. I can work with O of n into s, but I cannot work with O of n square. So the main factor is I have to reduce this. This reduction which we saw can be useful, but yeah, that is not much important. The much important factor was to reduce my O of n square. How I will do that? So let's see. So basically, if I am at some specific index and I have to go and find what index I should actually match with. So now I just tell you that what I am doing right now, I am actually adding or searching some word, because if you are at the S1, right? Firstly, you will have to add your S1. Okay, S1 is added. Now I have to search for my S1, search for S1 as a prefix and suffix in all these strings, in all the later strings. So can't I say one thing, that I'm applying kind of a same operation of adding and searching a word in my entire operation, or basically whatsoever I have to perform, I will add some word and I will search that word as a prefix and a suffix. So as we had already solved same kind of string comparison problems via try, so we got a hint, maybe we can solve it via try also. Again, if you had not solved the problem via try, please, I highly recommend, please go and watch this video, which is implement try. Just write implement try by Aryan Mittal, you'll get the video. Firstly, I'll recommend watch this video to actually understand the base or basically root of how try works, right? Then as a practice problem, you can try this problem, like design, add and search word data structure, right? In this you will see how adding and searching of a word happens in a try. Now the same funda, exact same funda, we will apply in the current problem, because it also says the exact same thing, that you have to add a word S1 and then search that word S1 as a prefix and suffix in your later part of the string. So now if I just represent, again, I am not writing the actual words, I'm just representing that as one square, like one circle. One circle is one character. So it's a blue, one character. So again, I know one thing, I'll add and search, I'll do that. So again, I remember that I'll add a word in my try. How you add a word in a try? Okay, you'll get on the first character, you will add that in a try. Next character, add that in a try. Next character, add that in a try. That is how you keep on adding in a try. Again, if you don't know how try works, please pause the video right here and watch this video or this video. Both will be very helpful. Now, if anyhow you know how a try is structured or works, you can just continue watching it. Maybe you can in the end watch those videos. Now, coming on back, let's say in the very beginning I had nothing, so I added these words, like I added this word one in my try. So blue, you can see it is here. Now comes the word 2. So now this searching part of word 1 in word 2 will actually happen simultaneously while I'm adding word 2 in my try. That's the most interesting part of try. So I'm adding a pink. Okay, pink first letter. Okay, I added pink next. I added pink next. I added. Oh, as soon as I added a pink next, I would have realized, bro, my word 1 ended at this specific portion and I am at the same try value, like I am at the same try path, and word 1 ended here, which means the word 1 is a prefix of my current word, which means I am iterating on word 2, but word 1 is a prefix of me. Bro, I wanted the same thing, so I can simply say no. Okay, I can increase my answer. I can increase my answer by 1. I'll imagine, okay, I am word 2, I have found a word 1 which is actually having a same prefix. But bro, one thing you are missing. You are saying that, okay, pink is matching with the blue, you have found the prefix, but your problem was saying not only prefix, you also have to match the suffix. Now, so far the problems look so simple, but now our task is that while moving on to the words, I can compare the prefix, because I'll simply keep on building my try and I can just mark at the end. I would know, okay, as soon as I am just plotting for the word 1, so as soon as the word 1 end, I can mark a variable, let's say is end as 1. I can mark that, right, is end as 2. So I can just simply say, okay, this is the end. So for sure, I can increase the count, my answer, by 1, because I have found one pair, word 1 and word 2. But that is only when I consider only prefix part. So again, there are two flaws in this approach right now. Firstly, I took is end. First flaw is I took is end. Why is end is not useful? Because is end will be a true or a false. But I'll tell you, like I ask you, what if I had another word 0 of the same length and exactly same? Then what? Will you say is end exactly same. Again, it's exactly same. Byte 1 is end. So for sure, at this location, is end should have been twice, right? Makes sense, because for word 2, the pair form will be word 0 and word 1. So two pairs are formed, not one pair. So you have to make sure, rather than is end, keep a count of how many words ended here. So I'll say 2 words ended here. So okay, one flaw solved. Other flaw was that it is only checking prefix. I also have to check a suffix. So Aryan, shall I make a opposite tree? As in, like, one way is you make the tree from the very back, which means you actually start iterating from the back itself of the tree. Shall I do that? Bro, you cannot. Why? Because for the same pair of strings, you have to compare that. Okay, for this word 0, for this, let's forget word 0. For this word 1 and word 2, you have to compare both. That like word 1 should be a prefix and suffix of the word 2. So you have to find some hack. What can be? We will just derive that. How we will derive that? Let's see. So we had a string 1, let's say A, B, C. We have a string 2, A, B, C, something in between, and then A, B, C. Again, I will try to build that how I can. Again, I know one thing, that okay, to actually match or compare my strings, I can use something as hashing because of Rabin karp. What Rabin karp gave a like helpful thing to me. So I know, okay, not exactly the Rabin karp, maybe I can use that, maybe, but still I can maybe hash stuff. That is one thing which I had already seen, but maybe it is useful in the try, because earlier it was a different structure altogether, but now it's a try. So now I have to go about in a try mode. So I'm in a try mode right now. What's a try mode? But yeah, so what I'll do is, okay, earlier what would have happened is that in a simple try, okay, I would have made my ABC. Okay, firstly I would have iterated my string 1. Again, remember, string 1 is on the left and string 2 was on the right. So basically you first got onto string 1 and then you got onto string 2. So basically I'm just trying to see that how my string 1 and string 2 can form a pair, in which string 1 should be a prefix and suffix of string 2. So I made a string 1, I made a B, C, right? Simple, string 1. Now when I was at string 2, I started making again. Okay, A I got, okay, A I got, B I got, B I got, C I got, C I got, E I got, okay, E I got. Then I can keep on making that. But again, Aryan, you are only comparing your prefix. Your suffix will never be compared, because to compare your suffix portion, okay, even if you make a E and then let's say something and then F and then A and then B and then C, but then here you compared with blue. Where is the blue here? Nowhere, because the tree will keep on increasing. It will never come back to root. So there's one thing, I cannot do that. But if I analyze one thing, what's happening? If you look back very closely, that how, if I'm saying this portion A, B, C is a prefix as well as suffix, then what happened? This A should match with this A because it's a prefix, and this C should match with this C because it's a suffix also, right? So can't I simply say one thing, that this AC pair should match with this AC pair, right? This again. Now let's move on. This BB pair should match with this BB pair. Great. Then this CA pair should match with this CA pair. Great. So what you learned from this, that again, this is something which was so great that we could have that we could figure out. Again, there's another like bigger way to solve it. Bigger ways, okay, actually use Rabin karp to make hashes, which we have already seen that we can do that. But now we actually start thinking the try mode. We were in the try mode, and then we tried to find a pattern. What was the pattern we found? Okay, A is comparing with A, C is comparing with C. So AC should match with AC. Then BB should match with BB. Make sure how I am marking. I am saying CA, I am not saying AC. Then CA match with CA. Right. So this is what I will do as a new improvisation. So what I will do is, okay, I will pair up. Rather than, again, previously I had one node, okay, A, B, C. So I was making a try of that one node, A, B, C. Now I will make a try of actually the hash value of these two pairs. AC, BB, CA, and so on and so forth. So I will say, bro, one thing, bro. you will make the first node. When I'm iterating on my string 1, I'll make the first node as not A but AC. Next node will be not B but BB. Again, how AC? Pointer I and J here. Next pointer is I and J here. Next pointer is I and J here. Specifically, I marked it so that you don't get confused. So it will be CA. Now, when I'm iterating on my string 2, then again, let's say I and J here, right? So AC. Again, it is matching with my AC. So now I can compare. So when I'm comparing, when I'm comparing the string, I'm comparing both prefix and suffix. That's so great. Now, okay, I is here. J is here. BB, compare BB. Yeah, it is matching. Okay, I is here and J is here. Compare CA. CA, yeah, it is matching. Oh, bro, it ended also. So increase the answer by 1. And as soon as it is matching, which means you will have a end. Okay, your string 1 ended here. So increase the counter by 1. Again, I'm not taking is end as a variable. I'm taking count as a variable because I know I will be ending multiple strings at the same point. So I should actually increase the count. So I'm taking count rather than is end. So I can simply say I can increase the answer by 1 because I have found one pair. If count was 1, so I had one string already, and I can also match the exact same string at the same point. So increase the count by 1, which means I have got one pair. Same way, let's say if I just increase that and I have a different string, which means string 1 would have been ABC. So by default, you would have made only A, B, and C, and then you would have start making A, B, E, and so on and so forth. But now we will use a hash. Or we will use a hash which will use both prefix and suffix. So I'll make a AC hash. Okay, AC, then BB, then BB, then CA, then CA. So I'll compare AC. Okay, AC, BD, BD, not matching, not matching. Now with this BD not matching, I never mean that I will stop and I'll not compare. I will still have to make the entire try. So okay, BD will be a new node. So it was a BB earlier, it was a CA earlier. So BD will be a new node, and then it will keep on going again. EA, okay, EA will be a new node, and thus a new tree node will be made, which will never be matching with the existing ones. So I will not increase my answer, but still I have to make the entire tree. Aryan, why entire tree? Because what if in future I'll get a word, let's say string 4, and that actually contains my string 3 as both prefix and suffix. So that should include increment my answer, right? That's the reason. Now, so we know that we use a try and hashing. Let's simply have a dry run on the existing example itself. A quick dry run. How? Simply, we'll go in the left right order. Why Aryan? Why left right? Because we know that okay, I and J, I should be less than J. If you had remembered in the problem, I have to take I should be less than J. So whatsoever is made previously, which is I, will actually be used as a prefix and suffix in my J, and J is afterwards. So that's the reason I am just taking in this order. There are many such small points which actually make this problem very good. So firstly A, okay, A, but remember, make sure you have got one A, but the actual try which you are making should be a combination of start and end, right? Yeah. So I'll simply make A. I have so both I and J are here. I and J are here, so I can simply say it will be a AA. The hash will be AA. Now either you can have this as a pair and stuff, but that will take more space. So I can just simply say one thing. I can simply convert this to one integer itself. These two characters, I can convert that to one integer. How are it? Simply hash, because I know a character A. Again, these are two characters C1 and C2. I know they will be only two characters, and for that I have to make a hash. I know the C1, character C1 is a lowercase English letter, right? No matter what, I know it has a limit. No matter what, it will be less than 128, right? This C2, it is also less than 128. So I can say one thing. Okay, bro, simple. C1, right? C1, it will be less than 128. Again, it is less than 128. It is also less than 128. So to make a unique hash, what you should do is, what's the value you have for this? Let's say the value is 5. Or let's say the value is let's say the value is D. Character value is D. Now D, I can simply multiply that by 128 and then add another character which is C2. Let's say that this character C2 was G. So I can simply add a G. So you will see these will never ever interact with each other, because G maximum bound is 128, and because of that reason I have multiplied my next character by 128, so that this character D will actually be shifted 128 and will never be touching this character G or any character in the lowercase English letters. So I can simply make a hash of these two characters, and with that hash, and I can just simply say, okay, the hash is very simple hash. Although if you want, you can also use a pair, but that will for sure take more complexity and more time, and again that can be very tricky depending upon how you make your childs of a trie. If you want to try, you should try. If you want to try try, you should try try, this specific trie structure. Try. Cool. Now, so we know that we simply convert that to a hash. So what we'll do is, okay, I have a, I'll make a. Now convert that to a hash. Okay, this specific a, okay, a, which means this again. Remember, that is nothing but my word of I, or let's say current word is W. So W of 0 multiplied by 128 plus W of n minus 1 minus 0. Again, 0 is the index I. So this will be the hash, and I know that this is the last character for this, so have a count of 1. Now again, answer is still a 0 because nothing was there already. Now I came on to my ABA. Again, is that same thing, A and A, simple made will be made. Again, I'll say, okay bro, it is already there. In after my root, my A was already there. Okay, so if it was already there, simple move on. I'll simply move on to that specific node. Now node, oh, count was 1. Oh, count was 1, which means I had previously something which was same as that of my prefix and suffix. So increase the answer by 1. Okay, sorry, I increase the answer by 1. When the answer is increased, simply bro, move on. Okay, when I say move on, please complete, okay, B and B. Okay, B and B, add that, and also keep on computing the hash. Again, hash same way. To compute the hash, it is same way. If something is I, if something is J, I know I will keep on moving forward, J will keep on moving backwards. So hash will be nothing but your word, let's say word of I into 128 plus word of J. I know in the very beginning my I will be beginning from 0 and J will be beginning from n minus 1 minus I. So I can simply say if I can have only one variable, for only one variable also, and I can simply say it will be replaced by n minus 1 minus I. N is the length of this specific word itself. Remember, right, that fact. Don't confuse it with the length of n, which is the length of all the word strings array. Cool. So this is how I can build the hash for every of my iteration of I. I can now keep on moving my I like this, I, and so on and so forth. Now, when my I is here, you simply know your J will be here. Or you can simply say if I is here, then n minus 1 minus I will be at this location, which is you can refer as J. So you simply make on your BB, then your AA, because okay, erase it, AA. The first A was from this A to this A, but last A was from this A to this A. Then you simply make this hash. And again, it was the last character, simply increase the count. Okay, bro, next one came as A. Okay, so firstly, A, again, first pair, A. Okay, bro, it was already there. If it is already there, bro, simply move on to that. Oh, bro, count is also 1. Bro, simply increase the count by 1. Okay, bro, simple. I'll move on to next B. Okay, BB. Okay, bro, BB is already there, bro, also. Okay, bro, simply move on. But no count. Okay, simply move on. Okay, bro, I'll simply move on. Now, AA, bro, AA. Okay, bro, I'll simply move on AA. Oh, bro, AA, I have a count of 1. Bro, no worries, bro. Simply increase the count by 1. Sorry, answer by 1. Okay, bro, I increase the counter. Now, okay, BB. Okay, bro, BB, I'll simply move on. BB. Again, make sure you compute the hashes. This is for the representation, but you have to compute the hashes itself. Now, simply, bro, last one, A. Okay, bro, AA. Nothing was there, but yeah, I made the hash. It was the last one, so I also increase the count. So now, so far my answer is 3. Now, okay, bro, last character is AA. Simply, bro, okay, if it is AA, then first hash will be, okay, AA. Yeah, bro, AA I already have. Great, bro, simply increase the count. Okay, increase the count. Great, bro. Then move on. Okay, move on. AA. If I move on A, oh, A is not there. So make a new node. Simple how a trie works. If something is there, go on to child. If not, then make a new one. So let's simply make a new one and make a hash for it and also increase the count for it so that in future someone can use that. And that's how you have seen that your answer is 4. That's a simple trie. Cool. Let's see the code. It's pretty simple. A pretty standard trie code. Firstly, we will have a long for just to have a small, don't have to write the long. I usually write ln. Why Aryan long? Because you know you have to return the answer as long because you have to return all the pairs. Pair is ij. You know the what happened. You know the length is 1e5. So n square is the number of pairs. N square will actually surpass your integer limit. So it's the reason you have to return long. Long will also have worked, but don't know why they have put long. But cool. One basic thing in trie, you have to make a trie node. Now the trie node has majorly 3 components. Trie node has majorly 3 components. One is the actual trie node value itself. So I can give the trie node value, which means I can give the trie node a character or a value to him. Then the trie node contains the child or the children for that specific trie node, which is nothing but, again, people usually put a list or basically an array of the children. Again, the children also should be a trie nodes. But here in this case, we'll take an order map. And usually you will see that in my code, in the very basic classes, I teach that, okay, make an array of, children of trie nodes. But as we go on progressively, I will always keep on using unordered map because it is very flexible, and even also like you can anyhow do anything with the unordered map. With array, you are restricted. You have to define size, you have to put like all that stuff. But in map, it is very flexible. So it's the reason we'll say, okay, for this indicates that, okay, for the root node, or basically for the node, the children will be all trie nodes, and this will be children. Representing, okay, for the node, the children will be an unordered map of node to a trie node. So I can simply represent that by that. Now I'll also have a count. As I showed you in a actual trie node structure, you will have 3 main factors. One is the value of the node itself, other is the children you will keep track of, and other is the is end or is flag or basically the count. Any of this you can have. Usually you have is end, but I told you it has a flaw. You have to keep the count. Now a simple structure, a simple constructor of a trie node, although if you want, you can just skip this entirely and you can initialize here itself. But in actual system design, it is not a good practice, and it is good practice to initialize your structures or basically anything in your constructor. So that's the reason I just used a trie node, although you can initialize that here itself, 0. But okay, no worries. Now comes the main function, which means your solution. But you have to implement this function. But usually you have seen that as soon as this function is called, its constructor should be called. And I know that I will have a root node. If you had remembered, you had a root node in the very beginning. That is fixed. And then the tree starts building on that top of root node. So I know one thing, that I will have this root node, which is a global variable. And then as soon as the solution is called, because I know this function should be called, but before that, the actual class should be there, right? Its constructor I will make, and then in that I will initialize my root node with a simple empty node. That is my root node, and this is the common structure which we follow. Although again, I'll say this is not required. Simply you can initialize your root node in this function itself, but we are following good practice of a trie, which can be followed in every problem. That is the reason I tell that, okay, be consistent with the approaches which you take. We will follow the exact same approach in all the problems. Again, it's an overkill. You can actually remove the entire thing and make a simple line that trie node star root equal to new trie node. That's it. One line. All these 3 lines are not required, but still we will write that. So have a consistent structure. Now we'll come on to the main portion, that okay, final answer. Then we'll go on to all the words in the sequence in which they are given, because we know that I word should come first and then J word. Then I will initialize my, I know I have to just get that word and plot that in my trie structure, and while plotting I'll know I will use I and J. J is n minus 1 minus I, so I know I will actually have a I and J is n minus 1 minus I. this will give me a hash value. Okay, hash value, which is the node value for me. For that node, like this is a node value for me, and I know that I have to put that node in my trie structure, which is initializing by the root itself, and I just take a new pointer, which is current. Root will stay there itself, because every new incoming word should start from root and then start pointing and plotting their actual nodes. So that's the reason I just take a new pointer, root current, that will use my root itself, which was initialized in the very beginning. Now my n is the word size. N is the word size. So each word size, because word is a string array, but each word size is actually, this is the answer. Like this is the actual word size for each word. I'll go on to all the characters of my word, and for all the characters of a word, I will say, bro, simply make a hash. Although I can take a pair also, but simply my node structure is from node to the trie nodes. So simply make a hash. So I'll simply make a hash by saying word of I into 128 plus word of j. J is m minus 1 minus I. Now I'll simply have a quick check that, okay, bro, if I'm at current, do I have this child node? If yes, then simply move on to that child node, because next character is coming up. If not, then simply make a child node. Okay, I'll simply make a child node. If not, I'll simply make a child node. Now, as you are iterating on the child and you have gone to the child, bro, if you have a count as 1 at that location, or basically any count at that location, simply add that count in your answer also, because you are forming some pairs because of the count. So add the count at that because of that current, and then simply keep on going, trying to build your answer and also trying to build your trie, and also parallelly computing your answer here itself. Now when this portion is done, which means your entire word, that specific word, again you have multiple words, because you have multiple word in a words array, you have multiple word. In that simply when one word is done, simply in the end just tell, bro, word is done, increase the count, because this current word is done, so increase the count by 1. And that's how I will do all of my words in this order itself. Order matters because I have to do I and j comparison, ultimately get the answer and return. Time complexity will be O of n into s, but in the very beginning I told you n into s is actually bounded by 5 into 185, and that is the reason it will work. And the same way space is also O of n into s, and that's how you can simply solve it. Cool. I hope that many of you guys were asking for this problem. I don't know why. I know it is 12 a.m. and no one, I did a screenshot, but yeah, no one will actually watch it at this time. But still, that's the reason I just bought it. Cool. Thank you for watching. Goodbye. Take care. Bye bye.